Hi everyone. So in this section, I'm going to talk about NVMe strategy. And again, Vince has presented prior sections, and this is the little bit more future looking. There's stuff that I cannot talk too much in detail.
We'll ask you about it anyway.
I just want to give some glimpse of what are the thought process that's going through in Vmax and in general in Dell EMC. Right. So where I look at this is just take a look at some of the technology transitions, right? So we are looking into media transitions. Both Vince and I have been around for a long time. We've seen hard drives of different capacities, different speeds. NAND flash, if you think about it, since 2008, you had SLC, MLC, TLC, planar, 3D, all those different flavors, and now transitioning into storage class memory, where it gives us different set of performance characteristics, endurance characteristics, and price performance characteristics. And then when we look at drive interface transitions, we started, when I started, it was all parallel SCSI, and then it was 88, and then fiber channel, and then we switched to SAS and SATA. And now what's coming up next is NVMe drive interface. And then in host interfaces, again, we talked about earlier, Vince talked earlier, is, there are like all parallel SCSI, and then there was, SCON, FICON, fiber channel, iSCSI, FCOE, all those things now transitioning into what it seems like NVMe over fabrics. In certain respects, these two, drive interface and host interface, you may treat them the same category, but from storage array point of view, there's some distinction, right? So one is our back end, the other is our front end, and that's why I treat them here, listed them separately, but in general, they're in the same category of technology transition that we have to look. And what's common across all these things is really the latency, all right? So let's take a look at the media disruption, right? So if you look at, performance axis on horizontal axis, and then price on the vertical, right? So on the top right, we have DRAM, and then nothing is to scale here, so just to group them together. And then storage class memory is somewhere closer to DRAM. And then in the middle, we have NAND flash, which is really the workhorse these days is at least for Vmax, it's 1 write per day TLC drives, and then some arrays use 3 write per day flash drives, and then what's on the horizon is really QLC drives that are expected sometime in the second half of next year with different performance characteristics, capacity characteristics, and potentially less than 1 write per day endurance characteristics. And the other extreme is really hard drives and the cloud object storage. That is really, it's possible to tether those things into storage arrays, but really going forward, what we'll be looking at is really the workhorse, which is really the NAND flash that is transitioning from SAS interface to NVMe, and storage class memory, which is really, starting as NVMe, and then there will be versions of it in terms of DIMM form factors on the memory bus. All right? So really, previously, when we looked at it, we had flash and hard drive. So now we're looking at storage class memory and NAND. And the key to connect these two worlds is really the NVMe and NVMe connectivity. All right. And the other thing is really the latency, focusing on the latency of these new media types. And what does NVMe bring? You may have seen this slide previously. Again, with hard drives, most of the time spent in accessing the data was in media access and less on the controller latency and the software latency. And as we transition to NAND, again, that media latency went down. And as we transition to NAND with NVMe, some of the controller latency and software latency will be reduced. But then with storage class memory with NVMe, we'll get to a very low access time to media. Okay, and so these are really the type of things that we are looking at in terms of focusing on reducing the latency in the array and access of the data. So the important thing is really, since we talked about internal Vmax architecture, it is a cached storage array. So the write IOs are handled by the global memory that really gives the latency from a DRAM. If you look at historically, we used to have 15-20% writes or 30% writes in extreme cases. But recently, when we look at read-write mixture of workloads, we are seeing and in some cases exceeding 50% of the total I/O being writes. Okay, so that's an important distinction because that has certain implications on the media in the back end, and I'll tell you why. And then, however, just because we have more writes doesn't mean that reads go away. Reads will still be there, and then therefore you need to be able to handle reads with the latency that's low enough. So therefore, really focusing on the read latency in the presence of writes is extremely critical. So that's for that purpose. What we have is we have an internal test that we qualify every single flash drive and the new media that comes to our attention. So what we do in our testing is to the drive on a bench. These are bench tests running FIO. We just use a Linux host to drive IOs. What we do is we issue writes and ramp up the writes as we continuously and concurrently do reads to the same drive. Therefore, what's happening is we are ramping up our what we call write pressure. We are increasing the write bandwidth going to drives. At the same time, concurrently, we are doing reads and looking at read response time. And we are plotting, in this case, read response time against that write pressure. Okay? The red one shows most of it like a typical SAS NAND drive that's running around maybe 12 watts of power level, right? So what you do is, as you push more writes, maybe around 120 megabytes per second of write pressure, the read response time is around half a millisecond. Okay? And then if you replace that NAND media instead of SAS NAND, if you do with NVMe NAND, we get the blue curve. Okay? What this means is that with the NVMe NAND, we can push more writes while not impacting read requests and read response time.
How much of that is purely the queuing of the protocol and nothing to do with the media?
There isn't much. For example, for reads, what we do is we do just single back-to-back reads. We don't queue reads. Okay, so just for that purpose, just eliminate all the potential.
No, but you are bottlenecking on the SAS.
That's what I was meaning on that.
The SAS bandwidth, true, right? So potentially when you are here, you are contending with that one. But in this region, you are really looking at real effects. And the other thing to point out is that this is not necessarily intended to be 24/7 write pressure, because at these levels of writes, the drives will wear out. What happens in most cases is you have bursts of activity that's coming in to the array that you need to be able to handle, reads as compared to writes. So, writes are fact of life. You have to do writes, but you have to also make sure that reads get the best possible response time.
Is part of that just because of the decreased load on the CPUs in the array? Because they've been showing.
It's not. I think there are, definitely the interface makes a difference. Queuing is important, and another important factor is with NVMe drives, we can run them at 25 watts. So all the write-related activity is power-driven. So the more power you can provide to the drive, the better or faster writes they can do, and then you can therefore reduce the impact of writes over reads.
Yeah, so it's the SSD controller CPU.
Yeah, exactly.
Right. And the important thing is, again, as we go to larger and larger flash drives, the density will go higher. Therefore, it is important to protect the read latency when we have a burst of writes coming in. Maybe an application is doing a dump of writes, right? So therefore, it's important to do this. And the other thing is that, remember, we are just striping data across many drives in the back end. So therefore, one application may be running in memory and dumping all their dirty writes versus another application running mission-critical reads and contending for the same media that's coming in from a write dump from another application. So it's the really multi-tenancy aspect of it is critical.
Striping across multiple drives also means the slowest of those multiple drives is the one that determines the latency.
Correct. So therefore, we have to be really, cognizant of that difference. And then the important thing is really as we transition to storage class memory, which is really what NVMe will provide us, is really it looks something like this white line, and it starts very, very low in this end, and then it stays low for a lot more than what I show here, exceeding a gigabyte a second of writes to the flash drive. To SCM drive. Okay, so really, for us, NVMe is a transition not only for NAND but also for a gateway for us to get to storage class memory to get this lower latency access.
So just one other thing on your diagram there. Obviously, as you move through TLC and QLC, the write performance is much worse. So when you say storage class memory, are you referring to things like Optane, or are you referring to NAND storage class memory?
Well, one thing, when we transition from MLC to TLC, actually surprisingly, we've seen better performance for writes. It could be because I think we've been focusing on it with the vendors, because vendors, we are very explicit when we talk to them, when they talk about millions of IOs that they can do on a single drive. We ask them, okay, that's very good, but also this is important. We want to measure the performance characteristics based on this. So they focused on it. So when we transition from MLC to TLC, we've seen improvements in write characteristics of this red line. Used to look more like this before. When we transitioned, we improved, and that was firmware improvements, potentially media improvements, and power increases as well. Because again, when we transitioned, we were able to increase the power levels in TLC as well.
Okay.
The SSD controllers have gotten better faster than the flash itself.
It's got worse. Yeah.
All right. So this is the last slide. So basically, the timeline in Dell EMC portfolio, we have some products already have NVMe, and NVMe-based arrays. You will see mainstream storage arrays having NVMe backend in starting in 2018 from Dell EMC.
Do you have a high-level overview of the management and control plane architecture, the different products like Viper and whatnot, how that all fits together? Also SRM, with how the Dell EMC storage ecosystem should be managed?
Yeah, we didn't bring a slide for that today. We can certainly get it to you. There's, as you said, a number of components available, and we're glad to provide you some of the information on that. We didn't have it in this deck.
Does your manager of managers still SRM?
Yes.
Right. And Viper is for automated provisioning of legacy 3-tier storage?
Right, the Viper controller components and such, yeah.
And
again, we see a lot of that moving into the REST APIs. A lot of folks have decided that, whether you're using Chef or whatever they're using, they're taking a lot of that on and changing how they do it. So us providing a tool that does things that they're automating already, we're more focused on the REST APIs and how do we enhance that and make sure that absolutely everything that they need to do can be done properly through those tools so that they can fit it in their organization however they'd like, and then offering them good samples of how to do that they can take and use as a base, or that they can adapt to exactly how they want to run the operations.
So the automation ecosystem, so you mentioned REST API, so you have a series of plugins that people can consume in different automation platforms, is that right? Like, for example, vRealize Orchestrator. Is there a...
vRealize pieces, again, there's a whole thing on EMC code that looks at how do you tie the REST API in with different pieces. We've got the Cinder adapters and all the other stuff. Yeah.
All right. So EMC code is the repository that you need to go to find that, is that right?
Yes.
Okay.
Yeah, it seems to me as the DevOps automation tools are gaining favor, the manager of manager that is Viper becomes less valuable.
Well,
as a VMAX guy, I would tend to agree. I don't think the Viper guys would necessarily agree, but
no, but
someday the Viper guys will call me and explain to me why I'm wrong.
Yeah.
All right. Okay. Thank you.